Even though this course is in computer architecture, we will spend a couple of videos discussing also how to create parallel programs as well as how to make them more efficient. So we'll start off by discussing at a very high level a couple of different programming paradigms that can be used to create a parallel program. First, though, we have to understand the difference between a process and a thread. So a process is a unit of computation that you have in a machine. And this unit process contains a unique process ID, which is unique for this process, and no other processes has this ID in running on the same operating system. It also contains some mapping virtual to physical addresses, which is also unique for this process. Furthermore, typically you have some kind of process global storage that is heap as well as static memory storage that all computation in this process can access. You also have some higher level descriptors like file handlers and so on that exist at the process level, and also typically a process has some kind of executable code associated with it. Inside each process, you have at least one thread of computation, and that's where the real work takes place. So the thread of computation has a thread ID, which is unique thread ID. It can have some additional storage, thread local storage, that only it accesses. It also has some execution context or state associated with it. So, for example, the contents of all the registers of the pipeline is associated with a thread, as well as this special register, the program counter, that tells which instruction to execute next. The thread also has its own private stack used to do functional calls and procedure calls. Inside each process, there is at least one thread, but there can also be created many threads to run inside this process. And so these threads are fairly lightweight unit of computation, since they don't have to set up any new virtual to physical mapping or new file handlers and so on. When you create a thread, you simply possibly you create some thread local storage if that's necessary. Otherwise, you just sort of set up a new execution context and a new way of handling the stacks, which is private to this thread. So creating a thread is a very lightweight process, creating and killing a thread. All these threads created in the same process will all be able to access the same process global storage. So this is sort of the shared memory that all these threads will be able to read and write in a coherent way. An application may have several processes, and each of these processes may inside have several threads running in parallel. Typically, processes communicate with each other using inter-process communication, or IPC. So this is not the same as instructions per cycle as we architects normally talk about. IPC here stands for inter-process communication. So it's a way of sending and receiving, sort of sending data between these processes' own private addresses. So as you see here, these processes, they don't share any data. They all have their own local process data, and the way to communicate, send values from one process memory to another process memory, is to use this inter-process communication. There is also at Unix and Linux level, it's possible to create shared memory between processes. So this can, for example, be used, be done by an mmap call, but there are other ways of setting up shared memory as well. But typically, when you just create processes, that means you don't have shared memory between them. I'm going to discuss a couple of different programming paradigms for creating parallel executions. So the MPI library, Message Passing Interface library, is a standard that's been around since the beginning of the 90s. It supports parallel programming at the process level. So this library supports ways of creating new processes. It also supports different ways of moving data between uh, the private memories of all these processes. And this is, for example, done by sending messages and receiving messages. So you explicitly will tell which other process you would like to send a message to, and that other process must explicitly will explicitly also say that it is expecting to receive a message from a specific sending process. So often these send a message, receive message are created in pairs in these kind of parallel programs. MPI these days often support yet another way of data movements between the processes, and that's what's called one-sided communication. So one-sided communication is sort of like put and get. So it's a way for more lightweight way for processes to read and write each other's memories, but only the part of the memory that's been set up in a way to allow this way of communication. In MPI, this kind of possibility of reading and writing into each other's memory is typically not a coherent way of doing it. So instead, you will read a value from somebody else's process memory into some local variable. And if you will not be able to monitor if that value you read in the remote process, if that value will change. So there's no coherent mechanism to track that. You simply can just rip a value or rather copy a value from a remote process into your own process memory. So that's a one-sided communication. You also have some kind of synchronization primitives. You have some kind of collective communication primitives, something called scatter-gather, reduction, as well as good old memory or good old barriers. We will not discuss these for now. We will not discuss these in detail. We will later on, when we talk about vector processing, we will get back to scatter-gather a little bit again. So that was MPI that created processes that typically communicated sending messages to each other, and then we had this one-sided communication where you could copy a value from somebody else's the memory of another process into your own memory, but only if that kind of sharing had been set up in a special way using the MPI library. The other two paradigms we're going to talk about are Pthreads and OpenMP. So Pthreads is also a library. OpenMP is an extension to compilers. These are two different paradigms, and both of them support parallelism at the thread level. So they have ways of creating threads, for example. And the threads that are created typically share memory with each other in a coherent way. So this is the traditional coherent shared memory that we've been discussing so far. Of course, you have some way to synchronize between these threads. There are some collectives here as well, so you can have some reductions, maybe some kind of barriers, and so on. And I should stress that you can actually mix and match all these programming paradigms. So you can, for example, write an MPI application, and you use MPI to create the processes and communicate between the processes using messages. But inside each one of these processes, you may create several threads using Pthreads or OpenMP. And this is what often is referred to hybrid programming, where you, at the highest level, use MPI to send messages, and inside the processes, you may use the shared memory paradigms, Pthreads or OpenMP, to handle the parallelism inside that process. I'm going to go through a very simple Pthreads example just to show how pthread is working, and should this is simple example, you will use a slightly more complex example in the next upcoming lab. So as I said, pthread is a library, so you have to include it. Similar to you include other libraries in your code. Here we defined a global variable saying the number of threads we would like to create is 5. And then we start to define the task that we would like to run in parallel. So the task takes one argument. It has a local variable, TID, and TID we're going to get from the argument that's passed to this function. And all we do here is to print hello world, it's me, thread number, and then you print what the thread ID number that you received as an argument. Of course, this is where you would probably put some more useful code if you were to write a real parallel program, and then you return the null if just to show that this execution terminated in a sane way. Okay, so now we created the task. The next job is to do the main of this program, and the main will try to create several parallel threads that all of them will perform this task. So here in the main, first we will use one of the data structures that's defined by the pthreads library. So pthreads T is the structure that keeps track of each thread that's created, and we then make a vector of 5 of these. Then we have another vector with some threads arguments. So and then we have some local variables. Come to a first loop, and this is the loop where we're going to create all those 5 threads we would like to execute. So we go in this loop 5 times. First, we just do some bookkeeping. We initialize the thread argument vector to contain the loop counter of this loop, and then we just do some print statement to figure out what's going on here. And then as the next step here, we will call another function that's defined in the pthreads library, which is the pthreads create. So here we will create each loop. Each time we go in this loop, we will create a completely new thread of computation. That thread of computation will execute the task code we just defined up here, and we will pass one of the threads arguments that we initialized over here. So we just simply pass the pointer to the I, and then so now we created all those threads, which means we will see hello world. It's going to get printed 5 times by the different parallel threads, and then at the end we wait for all the threads to complete, and we check to make sure that they completed in a sane way. So we do a pthreads join. So that is the third primitive we're using from this library up here in this simple example, and then we exit this program. So it's a very, very simple example here. Lots of bookkeeping going on. Well, I did add some extra print statements that were not strictly necessary here, but there's some bookkeeping. You have pretty good control over what's going on, but it's pretty verbose way of creating parallel code. So just because it's so verbose, some people came up with a proposal to called the OpenMP. And in OpenMP, you can do exactly the same thing as you do here, but you don't have to care so much about all the little details. Instead, in OpenMP, the same task of creating 5 threads may look like this. So here we simply just have a loop we walk in this loop 5 times, and then we just say hello world, it's me. So we do the print statement right there, and in order for this to be parallel, all I have to do is to add one comment, what's called a pragma in OpenMP. And this comment says #pragma OpenMP parallel 4. That's what it says, parallel 4. And then it says so that means that this for loop, every time you make a new iteration in this for loop, you should consider if you it's not a good idea to create a parallel thread. So here, just using this pragma, we will actually create 5 different threads that all of them will be printing hello world. And then we also define that each one of those threads should have their own local copy of I. Otherwise, this value here wouldn't have been printed in the correct way. Otherwise, if I had been a shared variable shared by all of those threads, we probably would have printed the last value. All of them would have printed the value 4. But now, since we have local I, they all print their own local value. Also, what we don't put in this code, but the designers of OpenMP decided, is that there should be an implicit barrier right here. So all threads should wait for each other to complete and join together without us explicitly saying so. So that is implicit in this definition of how to do this OpenMP parallel for. Here is a little more complex example that explains OpenMP in a little more detail. So we have a matrix multiply code. Looking at this code here, it's just a standard C code. It's a function that multiplies A and B and it puts the result in the matrix C. So we pass in A, B, and C, and we just loop. We have a 3 deep nested loop, as you would for this, just doing the standard matrix multiply implementation. So nothing fancy here. So this looks like a very sequential code, and it is. All we have to do now to turn this into a parallel OpenMP code is to put in the pragma, saying pragma, the next for loop should be done in parallel. And by the way, make sure that you have local variables I, j, k, and sum, because here you're going to possibly create as many parallel threads as up to n parallel threads, because each time you run in this outer for loop, we will possibly create yet another parallel thread that will do that job. And since there is no data dependencies between the actions done here in matrix multiply, it's it's as simple as that. So now we'll create up to n different threads here, where each of these n threads will do the j loop and the k loop and put all the results back into vector C. And of course, if we hadn't declared that I, j, and k and sum were to be local variables, that means that they would, all these parallel threads will start to write over each other's value of sum. But now with this simple statement over here, instead the compiler understands that each of these parallel threads should have their own local version of sum. Also, as in the previous example, we have an implicit barrier that's inserted at the end here to make sure that all those threads that have been created will have terminated before execution goes on. So it's a simple way of handling this. If you look at this code, there are lots of details that we haven't specified in this code. For example, I said that there could be up to n different threads created in parallel, but we don't know. Just looking at this code, we can't be sure actually how many threads are created in parallel. And that's some of the beauty of OpenMP, but it's also some of the disadvantages. We don't have explicit control, and that's what we gave up for the simplicity. Still, note that this code that I have here, we only added a comment. So for a C compiler, this looks, this will not be turned into nothing. So this code would still execute correctly, just using an ordinary C compiler, but then the matrix multiply will be sequential matrix multiply. And when you use a special OpenMP compiler or a compiler that can do both normal C and OpenMP, you pretty simply just set the OpenMP flag of that compiler, and by magic, this will become parallel code. So we looked at one of the pragmas of OpenMP, the OpenMP OMP4, and then of course we specify the local variables and so on. And this is a parallel construct to handle for loops. The other popular old-fashioned way of getting parallelism in OpenMP is to have a pragma called parallel. So here in parallel does not require the next statement to be a for loop for it to work. Instead, it will take, it could be, let's say that right after this pragma there would be 3 different calls to 3 different functions, and then this pragma would say do all these 3 functions in parallel. Another pragma, and this should be a good friend of yours, is what's called critical. So this is how you create a critical section in OpenMP. You're using a pragma, and you say the next couple of statements that I have singled out here are statements that I want to be done in an atomic way. So you should, it's the same as implicit, put lock and unlock around the critical section. But you don't do that in OpenMP. You just say this is a critical section, and then this lock and unlock will just be inserted implicitly. Same thing, there is a barrier. So there are lots of implicit barriers in OpenMP, but there's also ways for you to explicit put in barriers in the code. And then there's another pragma. Actually, there are lots and lots of different pragmas, but just one more that I wanted to talk about, and that's a pragma which is called flush. So flush is very similar to memory fence. So flush is a pragma that's rarely used, but but this is one you need to use if you were to write Decker's algorithm, for example. So as I said, it's a much longer list of pragmas, but this just gives you a taste of what kind of functionality is important in OpenMP. There are also some variable environment variables in OpenMP. So for example, I said that could be up to n threads created. The exact number of threads that would be created, unless it's specified in the program, it's actually controlled by this environment variable. So this is something that you can set in the shell, Linux or Unix shell. You just set this environmental variable, you run your code, and then you can change this variable and you run your code again, and now the program will behave in a different way. So if you set open num threads to 1, execute a.out, and then you set this, then you get a sequential execution, and then you set open num threads to 10, and you run a.out again without recompiling it. Now suddenly the runtime system will create 10 threads for you. You can also define how you want these threads to be scheduled. So if you want them to be scheduled in a round-robin fashion, or if you want them to be chunked, maybe you want the first 10 iterations of the loop to be placed in one thread, and the next 10 to be placed in the next thread, and so on. So then the chunk size would be 10, and you could specify exactly how you want these threads to be scheduled between the different cores on your machine. Of course, there is also explicit functions and calls to the runtime library itself. So you can write OpenMP codes that has more explicit controls over what's going on. For example, you can just call this function to find out how many available threads there are. So how many, what's the maximum number of threads you possibly can use in this machine. And then, after you know how many threads are available, then you can, inside the code itself, tell explicitly how many of these threads you would like to use for the next parallel region. So the parallel 4 or the OMP 4 or the OMP parallel, those are the 2 different regions we talked about so far here. You can also ask the runtime system to tell you how many threads it's using right now, and you can also ask the runtime system to tell you exactly which thread ID or thread number that each thread executing thread has. So this gives you much more flexible control, and this will sort of override the environmental variables, but will also create code which is much more OpenMP specific. Okay, that was OpenMP. I would like to take a look at this code, and there is something wrong with this code, and I want you to figure out what's wrong with this code. So as you may have noticed, it's the sum. The local variable list here doesn't contain sum. That means that all the threads created here will share the variable sum, so that they will overwrite each other in this statement over here, and that clearly was not the intention. Here's another question. Looking at this code again, and now we actually did fix the sum, so they should execute correctly. Looking at this code again, how many threads will be used? And as we discussed before, that is one of those things, unless it's specified in the program, which it is not here, that's one of those things that the environmental variable of OpenMP will decide.